Okay, in section 3.4 we're going to see how to handle the case where there are complex eigenvalues. So let's just do an example. Starts out like any other example. We don't know yet that the eigenvalues are going to be complex. We hope they're not, but they're going to be. So a matrix is this, and we have initial conditions, so let's actually solve the whole problem. So we start out just like in section 2, we try to find the eigenvalue, subtract 1 from the diagonal, set the determinant equal to 0, and we get lambda squared minus 4 lambda plus 5 is a characteristic polynomial. Use the quadratic equation to find the roots, and the discriminant is negative, which means we have complex conjugate roots. Now, we're always going to assume our matrix is real, so our equations are all real, initial values are real, and yet the eigenvalues can be complex, as they are in this case, but they'll always be complex conjugate pairs. So if 2 plus I is a root, then 2 minus I will be a root also. So the discriminant is negative. So we've got one eigenvalue. Well, that wasn't too hard, but now finding the eigenvector is a little more work, but it's still straightforward. The only difference between the complex case and the real case is you have to do complex arithmetic, basically. Well, that's the main difference. So we proceed as before, and we plug in lambda. Well, we just take one eigenvalue. Here's the trick. That's turns out we're only going to have to look at one eigenvalue and one eigenvector. We'll have a trick to avoid even looking at the other one. Well, the other eigenvalue is going to be complex conjugate of that, 2 minus I, and the eigenvector is going to be the complex conjugate of the eigenvector of this. So it's predictable, but in any case, let's just look at one eigenvalue and find its eigenvector. So we plug in lambda equal to 2 plus I, 1 minus 2 plus I, 3 minus 2 plus I, and 1 minus 2 is minus 1 minus I, and this is 3 minus 2 is 1, then minus I. So again, nothing different here, just now we need to solve that system. Well, if lambda was really an eigenvalue, then this system should be singular, which means the second row is a multiple of the first. So we haven't made a mistake. If it isn't, then lambda wasn't really an eigenvalue if we made a mistake. So you can basically, again, just ignore the second equation and find a solution to the first one and trust that the second equation is just a multiple of the first. Well, with real numbers, it was usually pretty obvious that the second row is a multiple of the first. Here it's not so obvious because the multiple is complex, so you just have to trust that you haven't made a mistake if you don't want to check it, and assume that this is the same as the first equation. So we have minus 1 minus ix plus y equals 0, and you can solve that for y and take x to be anything, for example 1, and y will be 1 plus I. So there is an eigenvector corresponding to that. Now if you take the second equation instead of the first, you'll get something that looks very different, but they'll both be eigenvectors. It's just that you can multiply any eigenvector by not just a real number but a complex number and still have an eigenvector. So you just have to trust that this one is correct for that eigenvalue. So we have an eigenvalue and an eigenvector, and the eigenvalue was 2 plus I, and the eigenvector was 1 comma 1 plus I. That's only one eigenvalue and one eigenvector. We don't have the general solution. We're just looking at one solution, one of the eigenvalues and its eigenvector. Well, what in the world is e to the 2 plus it? Well, it should be e to the 2t times e to the it, but what in the world is e to the it? Well, we have to use Euler's formula, which we'll justify below, but it's a well-known formula for e to the I times b, where b has to be a real number. It's just cosine of b plus I sine of b. So you just need to memorize that formula. So e to the 2 plus it will be e to the 2t times e to the it, and you use Euler's formula to take care of the e to the it because we have no idea what it is otherwise. So e to the it will be cosine of t plus I sine of t, and then there's the eigenvector. We multiply all this out, this complex times that, so we have cosine t plus I sine of t times 1, there it is. Cosine of t plus I sine of t times 1 plus I, you have to multiply by 1 and then by I and simplify a little bit, and it's this. And now we've got an I here and here. Let's separate it out so that we only have an I here. In other words, let's take the real part of this solution, e to the 2t's, multiplying both of them, but e to the 2t times cosine of t, cosine minus sine t, and then the I, e to the 2t times sine of t plus cosine of t. So notice that this is the solution for one of the eigenvalues, one of the eigenvectors. We know this is the solution of the differential equation, and the only place I appears is here. Well, here's where our trick is, and we'll justify it in just a second, but all I do, you have to get it in the form of a real solution plus I times another real solution. Once you have that, you can simply write down the general solution. It'll be A times the real part plus B times the imaginary part. Now, what in the world did we do there? We just got rid of the I completely, replaced it by a B, put an A in front of that. It's like magic, and there's our general solution, but how does that work? Well, it's explained in the book. So here's the justification. If you have a solution that is in the form of real function plus I times imaginary solution, now both of these are real, the only I is right there, then both the real part and the imaginary part are solutions. Why? Well, we know the whole thing is a solution. That means that y prime, which is the derivative of the real part plus I times the derivative of the imaginary part, is equal to y times that whole thing, real part plus I times imaginary part. And so if we know that the whole thing is a solution, then we know we satisfy that. But then this is complex function here, complex function here. The real parts and the imaginary parts have to be equal, so the real part here is equal to the real part there, which means that the real part is a solution. The imaginary part is equal to the imaginary part there, so the imaginary part is a solution. So that's why that little magic trick works. Basically, the idea is you just look at one eigenvalue and one eigenvector and manipulate things until the only place I appears is here. So you got something all real plus I times something all real. Then you can say, well, this is the real part of a solution, that's the imaginary part of the solution. They're both solutions, so A times the real part plus B times the imaginary part is the general solution. They're obviously not multiples of each other, they're independent. So that's an important trick. Whether you understand why it works or not, just get it into the form of something plus I times something, and then I disappears, and you have A times the real part plus B times the imaginary part. So there's the general solution. So that's everything, except now we want to plug in the initial condition, which was that when t is 0, y, the whole solution was the vector 1, 2. So you plug in t equals 0 here. E to the 0 is 1. Cosine of 0 is 1. So that's a 1. 1 minus 0. That's 1. 0. 0 plus 1. And that has to come out to be the vector 1, 2, because that was the initial conditions. So A is equal to 1, A plus B is 2, so A and B are both 1. So go back now, for that initial condition, A is 1, B is 1. So we can simplify a little by adding those two together, and we'll get e to the 2t times cosine plus sine. And down here we have cosine minus sine plus cosine. The sines cancel and get 2 cosine. So there's finally the final solution. Now, something a little funny here. We started out with a real differential equation with real initial conditions. We end up, of course, with a real solution. How could it be complex? And yet we had imaginary numbers running out the ears through the process. That's typical of the use of complex numbers. They're often disappear by the time you get to the final solution. They have to in this case, because clearly the solution has to not have any complex numbers in it, but yet use of complex numbers made this a whole lot easier to derive. And here's a little justification for Euler's formula. using Taylor series. If you remember your Taylor series, e to the x is a well-known Taylor series, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, blah, blah, blah. So you say, well, what about if x is just ib, where b is real, but I is a complex number? Then just plug in x equal to ib. X becomes ib. X squared is I squared, which is minus 1 times b squared. I cubed is minus I, so ib cubed is minus ib cubed. I to the fourth power is back to 1, so that's just b to the fourth. I to the fifth power is I to the sixth power is minus 1, and so forth. Now you get all the real parts together. That's the even terms are real, 1 minus b squared over 2 plus b to the fourth over 4 factorial, etc. And get all the odd terms together. They all have an I in front, so factor out the I out of the odd terms, and you'll see this is exactly, if you remember the formula for the Taylor series for cosine of b, this is the Taylor series for sine of b, so e to the ib is cosine b plus I sine b from the Taylor series expansion. So to review, if you have complex eigenvalues, it's pretty much the same as the real case, except you have to deal with complex arithmetic, which is much more difficult. First you find the eigenvalues, you get a quadratic equation, and you don't even know they're complex until you use the quadratic equation. Then you say, oh shoot, they're complex. So, but then the key is you just take one eigenvalue. Now how can you only look at one eigenvalue and one eigenvector and get the right solution? Well, it's because the other eigenvalue is the complex conjugate. The other eigenvector is complex conjugate of that, so it's not like you couldn't predict it. But anyway, you just take either one of the eigenvalues, find the eigenvector in the usual way, except that the second equation has to be multiple of the first if you haven't made a mistake, so you can ignore it and plug in x or y equal to 1 or anything you want and solve for the other, and you get an eigenvector. Remember, you can take any multiple of this and still an eigenvector, including a complex multiple. And then you use Euler's formula to take care of the imaginary part of e to the it, the imaginary part. So if that were 2 plus 3i, this would be cosine of 3t plus I sine of 3t. And so you take the real part, and then you multiply all this out, get it in the form of something plus I times something, where there's no i's in the somethings, then you're home free. Then you can just write down the general solution, and you don't even need to look at the other eigenvalue and eigenvector. Now notice that the real part of your eigenvalue, that both eigenvalues have the same real part. They're always a plus or minus bi. So the real part of both eigenvalues ends up in the exponential. The imaginary part ends up in sines and cosines. So looking at this general solution, you can see that this is a spiral source, because the real part being positive means you have e to the real t. That'll increase with time, so the amplitudes increase, and the fact that that there's an imaginary part just means that there'll be sines and cosines, which don't go to infinity or 0, they just spiral. So it spirals because of the imaginary part, and it goes to infinity because the real part is positive. Okay, 3 examples we're going to look at, and look at the phase plane. If A is this matrix, the eigenvalues are 1 plus or minus 8i. That's, you don't even need the quadratic equation here. It's 1 minus I squared plus 64 equals 0. Take the 64 on the other side and take the square root, and you get 1 minus I is equal to plus or minus 8i. So lambda is 1 plus or minus 8i, which means since it's complex, it spirals. Since the real part is positive, it's a spiral source. This one, the eigenvalues are minus 1 plus or minus 8i. This time the real part, which determines whether it's a sink or source, is minus 1, so it's a sink, and since it's complex, it spirals. And then this one, the real part is 0, so it spirals, but you got to e to the 0t out front, so it doesn't go to infinity or 0. So let's try all 3 of these and verify that that the origin 0, 0 is the equilibrium point, and all the problems in chapter 3, 0, 0 is the equilibrium point. But if the eigenvalues are 1 plus or minus 8i, it should be a spiral source. Minus 1 plus or minus 8i should be a spiral sink. 0 plus or minus 2i should be a center. So here's the first system. The matrix is 1 minus 8, 8, 1. And we predicted that would be a spiral source, and it is. Start anywhere and it spirals out. Okay, let's change the 1 to a minus 1 here and here. And now the matrix is minus 1, minus 8, 8, minus 1. That one had eigenvalues minus 1 plus or minus 8i. So that should be a spiral sink. And it is. And the third example, the matrix was 0, 2, minus 2, 0. The eigenvalues were pure imaginary. The real part was 0, so that should be a center. And it is. Spirals, but the imaginary part being 0, it doesn't spiral in or out, it just spirals. So at least the nice thing about classifying the equilibrium point, which is 0, 0 in all of chapter 3, but won't necessarily be in later chapter 5. Fortunately, you don't need the general solution and you don't need the eigenvectors, just the eigenvalues, which are pretty easy to calculate. So for these three problems, all we had to do is calculate the eigenvalues to classify whether it was going to be a source, spiral sink, etc. Okay, let me say something about systems of more than two equations and two unknowns. I said that everything we've done generalizes to larger systems, but we hardly ever talked about such a case. But I have a test problem where it had a 3 by 3 system. The components were x, y, and z. So it's x prime, y prime, z prime is equal to this 3 by 3 matrix times x, y, z. So x prime was minus 2x minus 3y plus 4z. Y prime is 0x plus 1y plus 4z. Z prime is 3z. Well, it's still true that the general solution will be, a solution will be e to the lambda t times eigenvector. So we need eigenvectors, and there normally would be 3 eigenvectors, that they're a lot harder to find for 3 by 3 systems, but we can do it easily with MATLAB. And so with MATLAB, I just say EIG of A, and it gives me the eigenvalues, which are minus 2, 1, and 3. Well, actually, that's obvious since this is upper triangular. The eigenvalues, you can read them off the diagonal, so we could actually figure that out without MATLAB's help. But in more general 3 by 3 case, you couldn't, and you can use MATLAB to find the eigenvalues. That means that one solution is e to the minus 2t times its eigenvector, one is e to the t times its eigenvector, one is e to the 3t times its eigenvector. And by the way, MATLAB can even give you the eigenvectors there are the eigenvalues again, and these are the columns are the eigenvectors. This is the eigenvector corresponding to minus 2. This is the eigenvector corresponding to 1, eigenvector corresponding to 3. It's normalized so that the sum of squares is 1. You multiply this by any constant and you'll get a eigenvector. So the general solution then would be a times e to the minus 2t times vector 1, 0, 0, plus b times e to the t times this vector, plus c e to the 3t times its vector. So there's your 3 arbitrary constants, and you can choose those 3 to satisfy three initial conditions. So 3 by 3 works pretty well the same. Now what is this? Well, one is negative and two are positive, so it's sort of a saddle point. If they're all three positive, then it goes to infinity. You know, the origin is 0, 0, 0. The equilibrium point is 0, 0, 0 again. If all three eigenvalues are positive, it's going to, the solution's going to go off to infinity unless you start exactly at 0. If they're all negative, it'll go into 0. Here it's sort of a saddle point, 1 negative, 2 positive, and that means basically it's going to go off to infinity for almost every choice of starting value. Now if they're complex, well, it's harder to describe what's going on, but the general solution is still you take e to the first eigenvalue t times first eigenvector and so forth, and linear combination of them. So it's pretty much the same as for the two-dimensional case. In fact, this test problem, actually I gave the eigenvalues and the eigenvectors and initial conditions, and so the student just had to find A, B, and C, which made it satisfy the initial conditions. So ended up solving a 3 by 3 system.